This is the Mining and Metallurgical Society of America, and we have a webinar series. This is the beginning of our series on battery minerals. MMSA is an association of mineral resource professionals whose members represent all facets of mining and metallurgical interests, both domestic and internationally. MMSA has always been a cohesive group of senior people from the mining industry, minerals industry. The Society is dedicated to increasing public awareness and understanding about mining and why mined minerals are essential to modern society and human well-being. And today's webinar certainly follows that path. The Society concerns itself with fundamental principles and with problems facing the industry in such areas as legislation, economic and education, as well as environmental concerns, labor relations, and health and safety. Representatives of the Society from time to time testify before legislative bodies and provide advice to federal agencies. I'm Betty Gibbs, and I'm a former MMSA Executive Director, and I'll be leading the webinar today. I will introduce at this time Curtis Clark, who is the chair of our QP Enhancement Committee, and he will introduce the title, and also Simon Jowitt, our speaker. Okay, Curtis.
Good afternoon. Oh, thank you. Thank you, Betty. Good afternoon, everybody. And thanks for joining us today. The QP Enhancement Committee is formed with a mandate to research and provide information to members and interested parties throughout industry on subjects of interest, specific metals from time to time, and of course, as Betty mentioned, any legislative changes or modifications that were on the horizon. This afternoon, Dr. Simon Jowitt has agreed to speak with us. He's currently the tenured director of the Ralph J. Roberts Center for Research in Economic Geology and the Arthur Brandt Chair of Exploration Geology at the University of Nevada, Reno in Nevada. As a geologist, he has been very active in research about global mineral resources and the security of supply of critical elements, among many other interests. His talk today will be a little bit wide-ranging, but of specific interest to the topic du jour of critical minerals. A little bit of housekeeping. Questions can be entered into the chat for this webinar. If you have an urgent question, please raise your digital hand and Simon will address it immediately. But any other questions, please put them in the chat and we'll address them at the end of his address. All our webinars are uploaded to YouTube and can be accessed through the MMSA.net website, and a video of this webinar will be on the website within a week. The MMSA webinars are supported by the Jacqueline Foundation. Dr. Jowitt, thank you for being here today, and we look forward to your presentation.
Thank you for the opportunity. I'll just begin by sharing my screen and we can get underway. Hopefully you can all see my presentation now.
Yep, looks good.
Excellent. Okay, so yeah, today I'm going to be talking about nickel and the energy transition, and discuss a kind of, or provide a bit of an overview of current nickel resources and reserves, where we produce nickel from in the past, where we're likely to produce nickel from in the future, kind of balance of supply and demand, and overall implications of all of this for the future of the nickel sector. We know that nickel is fundamentally important to modern life and society. It's crucial for things like the production of stainless steel, specialty alloys, electroplating, and that's been the case for a number of years now, a number of decades in some cases. And battery production is also an expanding market for nickel that I'm going to be talking about in the near future. The global demand for nickel is expected to rise rapidly as the world transitions towards a carbon neutrality, if you want to call it that, or a low to zero carbon dioxide and carbon neutral energy and transport future. But the balance of, as I'll talk about, the balance of or the timing of demand and supply changes remains somewhat uncertain. And it's this kind of balance of supply and demand, and whether we have undersupply or oversupply, depending on this balance, is going to be crucial for nickel, but also for a range of other commodities and sectors that are affected by the energy transition. We know the future is going to necessarily involve the greater use of batteries for energy storage associated with the renewable energy systems. There's almost certainly going to be greater demand for nickel, but there are uncertainties in that. And there's uncertainties on what exactly the makeup or composition of batteries that we're going to use in the future are going to be. There's a lot of people talking about lithium-ion batteries, but there's a lot of people looking at and talking about alternatives as well. And the exact composition of the cathodes in those lithium-ion batteries, which is where the nickel is contained, is again somewhat uncertain. And nickel, some of you might know, it's sometimes called the devil's metal. Saxon miners in Germany, maybe 500-600 years ago, found what they thought were rich ores. They called them kupfer nickel or devil's copper. That they didn't produce valuable metals like copper, but instead yielded this thing called nickel, which in essence 400 or 500 years ago they had no use for and couldn't readily extract. So we know that the World Bank, the International Energy Agency, suggests that global carbon neutral energy generation and storage and transport demand for nickel by 2050 is going to equal nearly 100% of current production, or production maybe a couple of years ago. In other words, there's a likely chance that we need to double the amount of nickel we mine, and we need to find that nickel, we need to put that nickel into production, and we need to ensure that we extract it in environmentally and socially acceptable ways. This also means that understanding the current nickel market and known nickel resources and reserves, in other words, where we already know nickel is in the ground and where it's likely to provide a significant proportion of that future supply, these are key factors in enabling the energy transition. Includes, we need to also think about things like environmental, social, and governmental or governance challenges that may prevent nickel project development or hinder current operations. And this is a key challenge for the entire minerals industry. And there has been some influence on this in the nickel sector, as I'll talk about later. The overall transition, the energy transition I'm talking about, is being driven by climate change mitigation, but also it's being driven by consumer demand. People do want Teslas and things like this, and they have the raw materials that make those vehicles need to come from somewhere, including a significant amount of nickel. But there's also a lot of investment spending and demand, not just by governments, but by private industry, which again is driving some of the supply or some of the demand increases we're seeing relating to the energy transition. But before I jump into nickel specifics, I just want to provide some kind of wider context on what we see in terms of metal demand and what the likely impact of the energy transition is going to be. So this is a slide I like showing. On the left, we have a 1980s unsmartphone, a brick, and the range of elements we used to use in technology in the 80s and to some extent the 1990s. On the right, we have a smartphone, the thing that most of us have in our pockets, and the range of elements we use in a typical piece of modern technology. In essence, what we've done is we've doubled the amount of minerals and metals we use in modern technology to give us smart capabilities of various types, or to just to improve the efficiency of whatever it is we're using. And this is not just phones, but this is kind of every aspect of modern life. You see this more and more in vehicles, in computing, in essentially the everyday technologies we have. I mean, you can even get things like smart fridges and smart washing machines, which again reflect, the reason that it has those smart capabilities is the fact that we've essentially doubled the amount of metals and minerals and elements we've put in these technologies. In other words, what we've seen over the last 10, 20, 30 years is a rapid increase in the metal and mineral intensity of modern life. And you can see that in the diagram like this. So this is just a diagram showing mined metal production from 1956 through to more or less the present day, all normalized to production in 1956. So in other words, if we produce exactly the same amount of metal or these minerals here that's shown here, that as we did in 1956, in other words, there's been no increase in demand, then what we would see is everything lying along this dashed line here that indicates this kind of one value, the value that we mined in 1956. What you see is a general trend of everything increasing up to the right. Some rapid increases, some not so rapid. This is a logarithmic graph, so it's anything that's up here. So things like the rare earths, lithium, and so on. That you were seeing certainly rapid increases in these. And this line here, the squares here actually show nickel. So we in essence mine a significant amount, 10 times more nickel than we did in the 1950s. Which isn't very surprising if you think about kind of global population and so on. But the other thing is that with a few wobbles down here, and with the exception of arsenic, everything else is increasing up to the right. So we're just mining more of essentially most minerals and metals than probably any other point in human history. But if we also think about normalizing this in another way, if we think about normalizing it to per capita, on a per capita basis, in other words, per head of human population, we still see increases up to the right. So, what we've got is essentially nickel here, around 3 times, or every person on this planet uses 3 times more mined nickel than they did in the 1950s. So that means that even with increases in population, it's not just that that's driven the demand for these metals that we see here. It's actually the fact that modern life is more mineral and metal intensive than probably at any other point in our history. And this also needs to be borne in mind that we're recycling a lot more metal than we did in the 1950s. We recycle a lot more nickel than we did. That means that some of the demand side of things is actually met by that recycling of nickel. But the fact is we still need to mine more nickel than probably any other point in our history just to meet that metal and mineral intensity of modern day life. This is like the underlying trend before we even think about the increasing demand from batteries and so on that I'll talk about shortly. So that's the kind of baseline. That increasing trends we see in most metals is the kind of underlying trend that reflects the underlying demand for metals and minerals of modern day life. And we can talk about current resources and reserves of metals, but we need to understand what's changing. Why are we expecting an increase in demand for nickel? We already see there's an overall increase in demand, but we're expecting that demand to accelerate. And it is this global movement towards low and zero carbon dioxide energy generation, storage, and transport that I mentioned. That's driven by investment demand and climate change mitigation and demand for consumers for technologies like electric vehicles. What we need to think about is, well, what does all this mean for nickel? How do we use nickel in these technologies? What of these technologies are important in terms of nickel demand? If we look at the initial use of mined nickel, what we've got here is essentially at the moment, maybe a bit more than this now, this is a couple of years ago, these data from the Nickel Institute, we might use about 5 or 6% now of a global mined nickel that goes straight into batteries, probably even more. Nickel plating, alloy steels and casting use a significant amount, non-ferrous alloys, and the vast majority of use is stainless steel. We're expecting this 3% to probably jump up to 30 or 40% in the next few decades, and this is where significant growth in nickel demand is expected. It's in these batteries. And you may or may not like Elon Musk, but the fact is he has got a good turn of phrase at times. Him describing Tesla batteries, our cells should be called nickel graphite because primarily the cathode is nickel and the anode side is graphite with silicon oxide. There's a little bit of lithium in there, and people talk a lot about lithium, but it's like the salt on the salad. So the lithium is the thing that makes the battery work, but the actual majority of that battery, the cathode side at least, is nickel. We know that nickel is important in lithium-ion batteries, and these are 2 examples of modern battery compositions. NCA is nickel, cobalt, aluminum, or aluminium, depending on where you are in the world. The cathode in that battery is 80% nickel, 15% cobalt, 5% aluminum. And NMC, this is an NMC 811, so 80% nickel in the cathode, 10% in the manganese, and 10% cobalt. So this just shows that the modern lithium-ion batteries contain a significant amount of nickel that enables those batteries to work. The cathodes in these batteries, a significant proportion of lithium-ion batteries are made predominantly of nickel. We're seeing increasing demand for these batteries globally. This is an example just down the road. This is from where I am in Reno. This is the Sparks Gigafactory. This is, I think, the largest building on the planet, or certainly one of the largest buildings on the planet, entirely devoted to battery manufacture. It has a capacity of 35 gigawatt hours of battery cell production a year. It's not always running at full capacity, but it's the equivalent to 500,000 Teslas and other, or the equivalent amount for home energy storage solutions. If we think about the demand from this one facility, if it only produces what we call NMC 811, so that's nickel, manganese, cobalt in the proportions of 80%, 10%, 10% in the cathode. If you think about full capacity, this factory, this manufacturing facility, it would need about 4,000 tons of lithium a year, 3,290 tons of cobalt, around just over 26,000 tons of nickel, and about 3,000 tons of manganese, and an awful lot of graphite to generate the anodes within these lithium-ion batteries. Global nickel production in 2022 was 3.3 million tons, a significant increase. But even with that insignificant increase, a facility like this producing NMC 811 batteries would consume nearly 1% of global mine nickel production, running at full capacity. Proposed battery compositions like NMC 955, which is a cathode where it's 90% nickel, 5% manganese, 5% cobalt. If we shift towards more nickel-rich cathode compositions, that means that there's going to be even more demand for nickel, just as a result of these battery facilities. And this is one of 300 of these facilities that are completed, underway, or planned globally. So there's a huge amount of development going on in terms of battery manufacturing because of the expected demand for lithium-ion batteries for vehicles, but also for things for like a grid-scale storage associated with wind turbine and solar panel deployment. If we look at North America, this is planned to develop battery capacity in terms of annual gigawatt-hour production capabilities. An awful lot in Nevada, 137 gigawatt hours. So that gigafactory I showed is just a proportion of that. A lot in California, a lot in Texas, a lot here in the kind of the eastern side of the US, some in Canada and some down in Mexico. And this is just North America. Europe is doing the same. South America is doing some of this. China and Asia is doing quite a lot of this and already has a lot of battery capacity already. So this is just showing this is where we're expecting this nickel demand to come from. It's all from these battery manufacturing facilities. And this is what some people, this is a benchmark nickel, this is benchmark looking at essentially nickel forecasting. So this is looking at essentially this is total non-battery demand predicted, and this is a total predicted nickel demand is the top of this curve here. This is the proportion of that demand that's made up by batteries. So this is by 2030, you're talking maybe 25% of global nickel demand will be or is predicted to be for batteries. Here we are in 2023, total battery demand was predicted to be 3 million tons. We've actually produced 3.3 million tons. So one issue could be that even though we're seeing this predicted increase in demand continuing off out to 2030 and beyond, the fact is we may already producing slightly more nickel than we actually want. Let me rephrase that. We're producing too much nickel. Nickel may be in a short-term oversupply situation because of increased supply from Indonesia, and that means that we know this demand is going to increase, but the demand and supply sides of the supply chain are kind of out of lockstep, which changes or makes prices more volatile for certain metals, including nickel, as I'll talk about later. And this is just showing another example. So this is looking at essentially the same nickel production. We have this is nickel consumption or estimating nickel demand. This is a nickel production based on current resources and reserves. But one thing that resources and reserves can do is expand as well as be depleted. And I'll talk about that later. So we're in 2023, 2022, we produced 3.5 million tons of nickel. So we're actually up here ahead of the curve or ahead of the predicted demand curve here, which again is causing potentially one of the causes of some volatility in nickel prices right now. So some of these predictions, this prediction wasn't too long ago at all. This was done in the late 2010s, but actually this prediction is kind of off because we've already exceeded production above what was expected according to this curve here. So again, this is just showing that if you just use current or given reserves and resources, these are an important guide We need to understand how resources and reserves can expand, and not just things that get depleted over time. And I'll talk about that again in a few slides' time. This is the World Bank's prediction. So what we're looking at here is 2050 annual demand, not total demand for the energy transition, but annual demand from energy technologies alone as a percentage of total 2018 production. So here we have nickel. What we need to do, if we're thinking about by 2050, we need to essentially double the annual production of nickel, or add another 2.3 million tons of nickel production per year to what we currently do. And that's one of the major challenges. And this is a longer term view by 2050, which is a fair distance away. But the thing is, if we don't have that nice balance of supply and demand, and the price and the resulting price volatility that we're seeing, that could actually hamper developments, certainly on the supply side. And this just puts those numbers into the previous graphs into numbers. We've got our 2018 annual production. Note that annual production of nickel was 2.3 million tons. Sorry, 2.3 million tons in 2018. In 2022, it was 3.3 million tons because of ramping up in Indonesia. Predicted demand from energy technologies alone is about 2.3 million tons again. So what we need to do is essentially by 2050 get to something like 4.6 million tons of mined nickel per year to meet predicted demands from energy technologies alone. And this doesn't include any ramping up of things like stainless steel for potential extra use in hydrogen storage and usage and so on. So there's other demands that could be in the nickel sector that we're not thinking about here. We just primarily think about batteries. So again, the uncertainties around all of this are something that needs to be thought about and ideally quantified before we kind of end up going down the wrong route, or presuming we're going to have oversupply or undersupply at certain times. And this just shows one example of why we're having that demand for metals and minerals and mining. So here we just have this is from the International Energy Agency. These are the range of metal used in a conventional car. Here in an electric car, we have a huge addition of extra metals and minerals because of those electric batteries, and a significant proportion of these is nickel. So this is where most of the demand comes from. There's some other demand associated with the wind turbines and so on, but the main extra demand we're seeing is essentially in transport and in lithium-ion batteries, the nickel-dominated cathode composition, as I mentioned earlier. So the question is, can we make a more than 100% increase, or at least a 4.6 million ton mined nickel demand increase to that figure by 2050? The question is, where's this going to come from? We understand the demand drivers. We understand that the supply and demand may not all from balance, and we'll talk about that shortly. But we do need to examine and think about the supply side. And what I've got here is some data that's essentially a global inventory of reported nickel resources and reserves for 2018. We published this database in 2022, late 2022, in Economic Geology. I can happily pass on the database of deposits that we've put together, as well as the associate paper. If anybody is interested, we can certainly pass on a copy, no problem at all. All the deposits we have in our database are classified by mineral deposit types, and that enables us to understand the relative importance of different mineral systems that are mined for nickel. The majority of nickel has been and will continue to be sourced from nickel laterites and magmatic sulfide systems. In 2022, it was about 50-50. That jump in production in Indonesia continued this trend where laterite production started to dominate over sulfide production. But one thing to note is that independent of the deposit type, what we do see, as we see in a lot of metals, is actually ore grades are generally decreasing over time. Other deposits have been mined for nickel in the past. Production from these remains relatively small, and the amount of production that we could expect from some of these unconventional nickel deposits, say like hydrothermal nickel, like down at Avebury in Tasmania, the likelihood is that these deposits may well be fairly small in scope, and certainly won't have the impact that bringing, say, or the impact or dominance that laterite and magmatic sulfide systems have had on nickel for the past 100 years plus. These graphs look at global nickel production. So what we have here is global nickel production split by country. You can see kind of back to the 1850s, we have production from Europe, then the rise of New Caledonia, Canada and the Sudbury field and other deposits, Australia, the Komatiites in Western Australia near Kambalda, certainly some deposits in the Americas. Indonesia here, and this Indonesian section will, if you actually had the present day data, would be significantly higher, as Indonesia is now the world's largest supplier of nickel. And then significant amount of production from the Russian bloc from the 1930s onwards. So this is Russia and the the Russian part of the former USSR, predominantly Norilsk and Talnak, but also deposits like Pechenga and so on. And you can see that the main players here are certainly Canada, New Caledonia, Indonesia, Australia somewhat, and Russia in terms of supply, with certainly an increase in production from areas like the Philippines, again reflecting the rise of laterites. The graph here, just the inset graph, shows nominal and real price of nickel over time. Nominal price, this kind of corrects for, this is the actual price, and this is the real price is corrected for inflation. You can see there's quite a lot of volatility in the last 20 years or so in the nickel price, and that reflects the importance of nickel to things like industrial development. So every time we have a global financial crisis, the demand for things like stainless steel decreases, and that means that the price of nickel slumps as a result. We saw that certainly around here, where we go from a high of getting on, well, at one point getting close to something like $50,000 a ton of nickel, then slumping as a result of that decline in economic activity as a result of the global financial crisis. If we look at where we get nickel from in terms of deposit type, this is just showing the proportion of nickel derived from sulfides and laterites. You can see early production from the sulfide sources, then the rise of laterites in New Caledonia. Sulfides hit back, if you like, with the advent of developments of Sudbury, and then we end up with this situation where, you know, in about 2018 or so, we have a 50-50 laterite to sulfide proportion, but this has continued on this trend upwards with the rise of Indonesian production, and certainly laterites are more important than sulfide sources of nickel right now. Whether that trend will continue is another question that we can think about, and certainly I'll have a look at some data that will examine that question of sourcing into the future. In terms of where we know nickel is in the ground right now, our database includes 626 individual deposits within ground resources and or reserves. Not all of these deposits have both resources and reserves. Some of them, or the massive majority, just have resources without any formal reserve estimation. These include 235 laterites, 342 magmatic sulfides, and 49 unconventional or miscellaneous deposits, things like hydrothermal deposits, nickel alloy deposits. So our ruite, this nickel iron alloy that has been identified as a potential resource in areas like Canada. Seafloor manganese nodules, there's at least one resource of the Clarion-Clipperton zone where nickel has been identified in seafloor manganese nodules, but again, as far as I'm aware, there's no reserve classification estimates for these manganese nodules yet. These nickel resources, these deposits contain about 350 million tons of contained nickel. If you convert all of this into resources, and production could meet about 106 years of nickel demand at current production rates, but this does not obviously include increased demand going into the future as we use more and more, or produce more and more lithium-ion batteries. Reserves are smaller than resources. That's always the case. They contain nearly 50 million tons of nickel, split into 26 million tons in laterites, 20 million tons in sulfides, and 1 million tons in miscellaneous or unconventional reserves. We actually produced a previous paper in 2014 that looked at 2011 data. We can actually compare individual deposits and think about how resources in those deposits are changing over time. Are they becoming depleted? Are they maintaining kind of status quo? So all the nickel they're producing is actually basically matched by delineation of brownfield resources. And the magmatic sulfide deposits, essentially, as I'll show shortly, we have a one-to-one relationship where every ton of nickel out of a given deposit on average is being replaced by the addition of a new ton of nickel in extra resources that are being delineated. That's on average. Obviously, project by project, there's significant variations. And there's also the discovery of new deposits. New deposits are being discovered of nickel globally. This also adds to potential increased supply. So it's not just the fact that we're maintaining our magmatic sulfide resources, but we're also actually kind of adding new resources via discovery. Laterites are somewhat different. Laterite resources and reserves are lower than 2011, suggesting near-surface deposits can be more comprehensively assessed during early stages of laterite resource and reserve estimation, and I'll explain that shortly. But the other thing to realize is that these numbers here are global minima. They're minimum values because some countries essentially you have poor reporting. Some mines are owned by private companies that don't need to formally report resources and reserves externally. So this is essentially, these are minimum values. We certainly may have missed some deposits as well. There may have been new discoveries since we compiled these data. But the thing to realize is that these are essentially minimum values. And these resources and reserves, as I'll show shortly, are dynamic. We're not saying there's only 350 million tons of nickel left in the ground. Far from it. These resources and reserve values do change over time, as we'll discuss shortly. This is just a grade versus contained nickel diagram. This is a global nickel reserves. You can see we've split deposits into essentially diamonds here, showing magmatic sulfide systems in the main, plus nodules in this color here. Laterites are shown as triangles. So you can see there's a clustering of a lower grade magmatic sulfide systems. These are essentially actually platinum group element systems like in the bushveld that produce nickel as a byproduct. And whereas the magmatic sulfide systems predominantly mined for nickel, these ones here, including this deposit here, this is Norilsk Taldak, so one of the largest deposits, even though it's been mined for something like 50 years plus now. If we look at resources are obviously larger than reserves. Again, we have the layered intrusions down here. We have a large clustering of laterites around here. We have Norilsk Talnak way up here, higher than everything else. But you can see there's certainly clustering of grades by deposit type, which is typically what you'd expect, and a very large range of deposits which are pretty enriched in nickel, and those down here where nickel is going to be produced as a byproduct of things like the platinum group elements and so on. If we think about current resources and reserves, it's important to realize that these are not all there is. So if we look at essentially the Sudbury Basin, producing from the late 1800s onwards, this is cumulative production of Inco and Falconbridge, turned into Glencore and Vale eventually, but from the original deposits that were essentially Inco and Falconbridge. What you can see is, total production by 2018 was getting close to 12 million tons of nickel. But the fact is, there's another, the reserves from Inco and Falconbridge, all their respective successors, are still, another 2 or 3 million tons. So there's still, after 134 years of mining, Sudbury is still a major world nickel resource. The fact is that, if we actually said, well, back here, these are the reserves, we've actually only got 8 million tons of nickel contained. When all of a sudden, we've gone way past that, and it's important to realize that discovery in this camp, plus also extension of brownfield extension of resources and reserves, indicate that there's still life in these mature mining camps after an awful long period of mining. These things are certainly mature, but there's an awful lot of mining, still an awful lot of potential nickel extraction and mining from Sudbury. It does also highlight the need to kind of distinguish things like geology and economics and the raft of complex social environmental issues. If you get something right, Sudbury at times has had issues with local pollution and so on, but if you get things right or sort things out, you can actually have really long-lived mining camps, mining success, if you like. But it's important to actually get these things right and think about the potential impact of environmental, social, and governmental or governance challenges as you develop projects. I've got the next slide shows examples from Minnesota, shows the impact of these environmental, social, and governmental challenges. But these are often hard to judge, but certainly need to be thought about more and more in kind of greenfield and even in brownfield situations. So this is just a couple of examples. Both of these deposits are within the Duluth complex in Minnesota. They're both nickel deposits with copper, platinum group elements, both very similar styles of mineralization, both somewhat similar sized deposits. The one on the left, because it's close to the boundary waters canoe area, had essentially basically mineral rights leases cancelled as a result of the potential environmental or perceived environmental impacts of mining. The deposit on the right is about 30 miles away, and that deposit is actually getting a bit of a boost from the Department of Energy, the same government, more or less at the same time, saying, here, have some funding to actually do some research into carbon sequestration and essentially looking at carbon neutral mining, or close to carbon neutral mining. So very identical deposits or near identical deposits, same mineralizing system, 30 miles away, different environmental challenges. One on the right, fewer environmental challenges and actually considered potentially environmentally beneficial. The one on the left, closer to the boundary waters canoe area, considered environmentally problematic and potentially running into hurdles towards development. And this just shows that, that some of the situations or some of the challenges that the minerals industry is facing globally, and that's, nickel is no exception to that. If we go back and think about resources and reserves and how they vary over time, so this is looking at magmatic sulfide systems. What we have is a 2011 resources for each of these projects. So each of these individual crosses here indicates an individual nickel deposit or nickel project. And what we've got is the resources that project had in 2011, and we've removed any cumulative production. So we've removed the effective production in terms of movement on this graph. And we compared to 2018, and what you see is a lot of deposits lie along this one-to-one line, y equals 0.994x. So on average, a lot of deposits are essentially producing material, but that production is being more than met by increasing in brownfield resources. In some cases, so the further we go to the left, the larger increase in resources we have coincided with production. The ones on the right may be moving towards depletion, but even then, you do see that there's still significant resources left, in even considering the 7 years of mining that's taken place in a lot of these deposits over this time. If we think about the other major source of nickel, laterites, we don't see the same thing. So the average line is actually further, it's y equals 0.91x. So in other words, what's happening is these laterites there's no real brownfield expansion, or not a significant brownfield expansion. And what we're actually seeing is deposits being depleted. And this may reflect the fact that nickel laterite systems are more easily defined earlier on. They're close to the surface, more fully delineated perhaps during the early stages of mining operations, and therefore less scope for expansion compared to magmatic sulfide systems, which could potentially have longer mine lives as a result of that brownfield expansion potential. So it's this interesting difference between magmatic sulfide and nickel laterite sources, and this has implications because we're getting an awful lot of nickel from laterites in Indonesia, and the question is, how long are the lifespans of those laterites in Indonesia and other places going to be? Some laterite deposits last an awful long time, I will say that, but others, on average, they seem to become more depleted, less potential for brownfield replenishment of resources than sulfide systems. And certainly this should be considered when we're thinking about future changes in nickel supply, what the deposit types are and how they can influence things like the brownfield expansion or brownfield replenishment of resources that have been converted into reserves and production. There's a few other things to think about with the nickel sector. Mining of nickel sulfides from ultramafic rocks. So this is an example of a tailings storage facility at Mount Keith in Western Australia. This deposit has a resource of more than 300 million tons. It's been mined for a fairly long time. But the deposit itself, the mining activities there generate around 11 million tons of fine-grained serpentinites dominated tailings a year, all stored in this facility. If you actually look at this facility, the serpentinite here is reactive. It reacts with the air to form carbonate minerals, and that actually naturally sequesters carbon dioxide from the atmosphere. So this tailings facility here sequesters about 40,000 tons per year of atmospheric carbon dioxide without any enhanced sequestration. That's just during normal tailings storage processes. That's around 11% of carbon dioxide produced by the mine site activities. The fact is, this is almost certainly the case for numerous other ultramafic hosted nickel deposits, comartite deposits in particular. Mining of these can effectively offset some of the carbon dioxide produced by those mining activities. And if countries like Canada or Australia, or potentially even here in the US at some point, move to carbon trading or carbon taxes, this means that the carbon sequestration potential of these nickel deposits, these nickel sulfide deposits, could mean that all sub-economic nickel projects actually become economic as a result of essentially policy changes. And if we move to actually enhance the carbon dioxide sequestration by, for example, laying down thinner layers of tailings in these facilities, then all of a sudden you can actually start to enhance the amount of carbon dioxide that's sequestered by these tailing storage facilities that are just produced or just required as a byproduct of mining. Other things to think about, I mentioned this earlier, this is decreasing grade. So what we have here is magmatic sulfides in different parts of the world and laterites in different parts of the world, New Caledonia, some mining in the US. What we generally see is a decrease in grades over time, which one reflects changing in mining style. We've gone to more industrial bulk tonnage mining. But the fact is, even in the kind of modern day when the mining styles are fairly uniform over the last 20 years, we're still seeing a decrease in ore grade, which means that these extraction of nickel and extraction of metals in any deposit, it means increasing energy usage, increasing carbon dioxide emissions, unless mines are electrified and use renewable energy or hydrogen and things like this. So this is just something to think about. If we're going to increase the amount of nickel we're producing, we're already dealing with a decrease in grades over time, and what the influence of those decreased grades going to be. I'm not saying we're going to hit the mineralogical barrier or anything like that, but certainly this could have this is something to think about when we think about the future of development of nickel resources and reserves that we already know about. There's other things to think about. So we know that nickel deposits can produce byproducts such as cobalt, copper, the platinum group elements. All of these are fairly well known. All of these add value to mined ore already. But there's significant potential for byproducts from magmatic sulfides and laterites, so selenium, tellurium, scandium, and also the potential production of some of these metals from unconventional nickel resources. The key here is understanding the potential, how these elements behave during mineral processing, and it's certainly worth investigating in some jurisdictions. So the US, for example, has tax breaks on critical metal production. Nickel is already a critical metal, but essentially, if you produce a critical metal from a mining operation, you can write off 10% of the cost of the production of that metal as a tax credit if you produce that critical metal. And nickel is certainly one, but if that changes, you still have the opportunity to get similar tax credits from things like selenium, tellurium, scandium, and so on, these byproduct critical metals that are already being mined, but in many cases are not being extracted. There's one example of this outside of nickel. Bingham Canyon, just outside Salt Lake City in Utah, has started to produce tellurium. They've known that tellurium is in the system for a while. Tellurium is a critical metal, so they're probably getting a tax break from the federal government, as well as funding to actually do research and the development of extraction facilities at the site. But the budget I saw for that tellurium extraction circuit was about $3 million, and the value of tellurium being produced was about $1.2 million a year. So in other words, that capital expenditure more or less pays for itself within 3 to 4 years or so. It's not a huge amount compared to the revenue for a mine like Bingham, but certainly it produces good news in terms of sustainability, in terms of the fact that this tellurium is going to go into solar panels. So it's not just the economic value, it's the environmental and policy value and social perceived value that may be worth considering if you're thinking about potential byproduct extraction from your metal mining operation, and certainly from your nickel operation in this case. And one thing to think about is just uncertainty in all of this. We talked about increasing demand, and we talked about kind of the supply challenges. So this is a nickel supply. This is a historical kind of mined nickel supply from nickel deposits globally up to about 2018. These are some models made in 2010 talking about different nickel demand trajectories. Basically, what we're seeing here is actually we're in 2022, we actually produced 3.3 million tons. So we're already way ahead of this curve of predicted demand, even or highest predicted demand. So the question is, how accurate are these models? What are the uncertainties here, and what the implications is? What we're seeing, if these predictions are right, is actually oversupply of nickel. So it's these uncertainties in terms of what the nickel demand is going to be and how quickly we can get supply into the market In Indonesia's case, it seems pretty rapidly. It's this balance and the timing of that balance of supply increases and demand increases that are going to be important going forward. This is just looking at the nickel price from essentially the start of 2023 through to a couple of days ago. What we see is essentially nickel prices going down, and this is all kind of flying in the face of that predicted increasing demand. But again, it relates to timescales. What we've had over the last couple of years is a lot of supply coming on board from Indonesia, in principle, in the main, but also from other countries. We had a significant jump in production in 2022, and that means that this kind of slump in nickel prices just reflect the fact that at the moment we probably have a short-term oversupply situation because that increase in supply has outpaced the increase in demand. That increase in demand is going to continue to accelerate, but at the moment it may be that we actually have an oversupply of nickel. It could be in 2 years we go back to undersupply because that demand increase is just going to keep on going up. So and now we have challenging economics for the development of mines because of this kind of short-term volatility or short-term oversupply. And this just puts that in context. So this is here we have essentially the last year, the start of 2023. That's that downward curve, but we are still above prices that we saw in 2020. There was a big spike around here and another spike here. So this is just things to think about. All of this reflects things like changing supply and demand, and we need to think about how this can influence things going forward. This spike here probably reflects policies relating to electric vehicles. We saw a larger spike in lithium and then a slump. So lithium prices spiked towards the end of 2022, then slumped through 2023. And that's because the policies around electric vehicles changed. People wanted to get tax breaks or tax credits on their electric vehicles. Those ended or changed at the end of 2022. So we had a significant amount of demand for lithium and for nickel, causing a spike here that we see, then a slump in demand as demand for electric vehicles, at least on the short-term basis, decreases. So what we need to understand is the potential impact of this volatility on the overall situation for nickel. And this just shows some of that volatility. So this is a whole range of different commodities, talking about yearly performance in terms of price increases or decreases from 2014 through to 2023. What you can see is this, I've just highlighted nickel here. So nickel in 2014 had a 7% price increase, down by 41% in 2015, up by 13%, 27, down by 16. So the main thing to take away here is there's been a lot of volatility, even in a large sector or fairly large sector like nickel. What you saw is 2022, lithium price spiked, as I said earlier. Nickel did the same, principally because of battery demand. Lithium in 2023 slumped hugely. Nickel as well, again, relating to demand from batteries, principally for electric vehicles. So it is this volatility, the supply-demand imbalances that we're going to see over short terms can cause volatility. And this is difficult for the minerals industry to deal with, especially as if you bring on a project, you've had a discovery, it'll probably take you 10 years to go from discovery to production, to go through all the engineering works, all the permitting and so on. And that kind of, in that 10 years, you could actually see, like here, a huge fluctuation in the prices of the commodity like nickel you're aiming to extract. So it's this volatility, short-term volatility, that could be really problematic if we're talking about increasing supply by bringing more mines on stream. I'm just starting to wrap up here. So overall, we know that known nickel resources and reserves are sufficient to continue current levels of production for several decades, assuming all material can be mined and demand continues at the same level. Not all resources can be turned into reserves and production. We know that there's an awful lot of resources that have just been sitting in the ground and been talked about for a long time without any activity. The nickel mining sector, like a lot of the minerals industry, does face a number of challenges that can change this. The fact that we can meet increasing demand. The increased demand we expect, at least over the next 20 or 30 years, is going to be higher than we've seen in the past as a result of the energy transition, this increased demand for nickel, in this case for batteries and so on. We also may see supply restrictions because of increased environmental, social and governmental challenges. The one question is, can Indonesia sustain increased production? Are there sufficient resources there for that to happen? And what are the environmental and social challenges in Indonesia like compared to the rest of the world? So these are somewhat open questions. The increase in laterite supply is certainly good for the overall nickel sector. Perhaps it's not ideal for class 1 nickel for batteries. Turning the nickel you get from laterites into the form you need for batteries requires more processing steps than is the case for magmatic sulfide systems. So this may be ideally suited for, or this increased supply could be ideally suited for stainless steel, but it's not ideally suited necessarily for battery needs. And what all this means is that, you know, global nickel resources and reserves do appear somewhat healthy and sufficient. Rapid increases in demand, limitations on conversion of resources to reserves to production, and limited supplies of what you might consider, battery-ready nickel could cause significant supply issues. And certainly, there's interesting times ahead in all sorts of commodities, as I'm sure you'll hear through the rest of this series of presentations. And one thing we could see is a nickel crunch scenario where nickel demand rapidly outpaces any increase in nickel supply, or even a shrinking of nickel supply, even with booming Indonesian supply right now. Class 1 nickel, as I mentioned, the laterite nickel is not ideally suited for battery manufacturing in the main. There's a potential for offset by positive developments in carbon credits for carbon dioxide sequestration by nickel mining in certain countries, and non-magmatic sulfide and non-laterite nickel resources, these unconventional resources. But one thing I will emphasize is the timing of demand increase is uncertain. The nickel sector, like a lot of the minerals industry, may have time to develop and advance projects and overcome challenges to development to meet increasing demand. But the timing of supply of increase can also outpace demand. We can have multiple mines coming on stream at once, which could cause short-term but problematic price decreases, or at least volatility that can cause challenging economics for nickel miners. And that could lead to undersupply of nickel for a short term as mines go off stream because the economics are poor. And then we get, again, a different form of supply and demand imbalance. All of this emphasizes that we know a lot about the nickel sector, but there's real need to understand the uncertainties associated with the energy transition and environmental, social, and governmental challenges to mining. So this includes the influence of policy. We just need to understand the implications of essentially decisions being made and the influence of these factors that, say, 20 or 30 years weren't really, 20 or 30 years ago, weren't really as important in the minerals industry and certainly in the nickel sector. And that's about all I've got. What I will say is, if you want some more information, feel free to obviously ask questions now, but you can always email me. I'll happily pass on the paper and database we put out a couple of years ago. There's some other papers we've had on nickel and this sector that might also be of interest. And I'd just like to thank the Nickel Institute for funding some of the research I presented in this presentation. And what I'll do is I'll stop sharing my screen and I'll happily take any of these questions if they have any.
Oh, thanks a lot, Simon. That was really interesting. We do have several questions in the chat, but I also have one question at the beginning, and that is, I know that there's a lot of development right now in recycling minerals from these batteries when they're depleted. And do you have any ideas or thoughts about how recycling may affect the supply at some point?
I think there's a lot of potential of increased, the more metal we put into the economy, the more recycling potential there is. And certainly nickel is one of the most recyclable metals we have, along with copper and the like. So there is certainly a significant amount of recycling potential. But the fact is, we're putting these metals in batteries in the main, and recycling of batteries is not something we're entirely familiar with right now. It's something that we need to do a lot more research and thinking about, a lot more development in, because there's going to be an awful lot of electric vehicles which are coming to their end of their life, and we need to do something with them. The question is, do we actually recycle the batteries, or do we, for example, take a battery out of a Tesla or a Ford electric F-150 or whatever, and then just use that with other batteries from other vehicles as grid scale storage solutions? Because the cycling of those grid scale storage facilities is a lot different to an electric vehicle, and it wouldn't require any recycling. You just take it out of one thing and plug it into another, and then eventually extend the lifetime of the battery, and then at some point you recycle that into the future. So I think there's an awful lot of questions over recycling. It's going to be crucial for lithium because the recycling rate of lithium right now is abysmal, but equally does apply to other metals like nickel that we're putting in the cathodes of these batteries. We need to be able to recycle as much as we can to make sure that things are not just one use once we mine them out of the ground.
All right, we'll go to the questions now. I have a question from Marco Carrasco, and he says, how about U.S. nickel mines? Are there unexplored areas? Is there any regulation that affects the development of those mines in the USA, environmental, social, or any other aspect? And is there any classification of measured, indicated, and inferred resources?
So, US, the main exploration for nickel in the US over the last, say, 20 years has been the Duluth complex in Minnesota and the associated, what we call the mid-continent rift magmatism, which extends from that part of from the US up into Canada. And you know, there is one active nickel mine in the US in Michigan, and there's opportunities there to develop some of these Duluth complex deposits, which are pretty big, but like I showed earlier, some of them have run into environmental and social challenges in terms of the development, primarily because of the proximity of some of them to these boundary canoe wilderness areas in that part of the world. Socially, I mean, it depends on which state you are in the US. Here in Nevada, we're pretty pro mining, and we're pretty happy for mining to happen. But if you look at other states like Maine, for example, they may not have much nickel potential, but they have lithium potential. But if you try and open an open pit metal mine in Maine, then the maximum extent of that open pit is 3 acres in size, which restricts kind of a typical mining that you might encounter anyway. So there's certainly lots of environmental, social challenges globally, and they do vary from place to place. Some places are more amenable to mining than others. There are other underexplored areas. We still need to know a lot more about the mineralization potential of the US. The USGS's Earth MRI program is producing a lot of pre-competitive data, but we're still, in terms of geophysical data, even geological mapping in some places, we're still, you know, maybe 20 or 30 years behind the Australians and playing catch up. But that means that there's a lot of potential out there to be understood and examined. So I think there's more potential for magmatic sulfide nickel than we know about. There's potential for some laterite nickel, maybe in California and Oregon still. And there's also potential for these aurorite, these iron nickel alloy deposits that are, again, in the kind of Klamath area of California. There may be some potential there that hasn't been evaluated as yet. In terms of measured, indicated, and inferred resources, we do cover that and discuss that in our database and associated with the paper. So we do have measured, indicated, inferred, and then proven and probable resource classifications where they're made available, and that's the majority of deposits we have in our database. So if you send me an email, I can easily send you a copy of that.
Yeah, we do have a couple of requests for the paper, and I'll send you those emails.
Sounds good.
Another question from Marco. Considering the demand for nickel, is there an alternative nickel substitute, a heat-resistant alloy based on iron, chromium, and aluminum?
The substitutability of nickel, like a lot of metals, is somewhat low. I mean, for stainless steel, there's nothing other than nickel that you can use. For battery cathodes, as I see, Alistair has a question next. I'll discuss that shortly. But in many cases, there aren't many alternatives, or the alternatives are even, you know, especially with metal prices right now, are certainly more expensive than the things we use nickel for already. So there's no real chance for substitutability in a lot of cases.
Okay. Alistair Horn asks, how sensitive is the projected growth in nickel to battery technologies? Is nickel required in cathodes, anodes, regardless?
It's very sensitive. So lithium-ion batteries, an awful lot of production is essentially nickel-dominated or nickel-rich cathodes. But there are also lithium phosphate batteries, which don't require any nickel. And there's other alternatives like sodium batteries and so on that are in development that, again, may not actually need any nickel whatsoever. But it all depends on the use of the battery, because the lifespan of a battery under different uses varies significantly. So we know that, earlier on electric vehicles used lithium phosphate batteries, but they may not be ideally suited for the kind of the better performance that's being demanded of electric vehicles now. And that kind of energy density and repeat use is why people are adding more nickel to their cathodes. It's the performance availability of EV batteries that contain nickel. That means that nickel dominated compositions are becoming increasingly popular, and we may be even moving to putting more nickel into our cathodes just because of the better performances that those lithium ion batteries seem to have at least in electric vehicles. Electric vehicles are not the only ways we use batteries, but I think right now I would say that lithium ion batteries in electric vehicles are going to be nickel dominated for the foreseeable future. Although I will say that with a caveat in that, if I knew that for certainty, I wouldn't be giving this presentation. I'd be sitting on a tropical island drinking out of a coconut because I'd know the future. So.
All right, thanks. We have several participants who appreciate your presentation, and I won't read all of those. You will get a copy of these so you have some, you can see how much everybody appreciates your presentation. I do have several things from Debbie Strusacker. Have you evaluated the comparative environmental footprints and energy consumption between sulfide and laterite deposits?
I haven't, but one of my colleagues in Australia has. So I know Debbie has a few comments there. So what I would suggest, Debbie, is if you can send me an email with your questions, and I saw you had a request for the graphic as well. If you send me all of those, I'll reply in an email, and I can provide you with the paper. I think Stephen Northey and others did life cycle assessment on nickel deposits, actually looking at very much that environmental footprint and energy consumption. So I'll be able to dig that information out for you and provide you with a slide with a graphic if that works for you.
All right. She also says the Biden administration was able to withdraw the leases. I believe the Tamarack deposit is on private and/or state lands.
Yeah, I think that's the case, and it's interesting because the kind of here in Nevada, obviously we have a huge amount of federal land, and that's one thing that actually makes things attractive because it's fairly accessible. People can go on and stake claims according to the I'm going to get the date wrong perhaps, with the General Mining Act of 1872 still, and that's one thing that makes things very accessible out here in the West. But there is always that chance that the federal government could remove your mining or your prospective area from consideration for mining activities for environmental or social reasons or things like that. So there's pluses and minuses to being on state land, on private land, or on federal land, and it can be both an attraction and a negative in some cases.
Darby Stacy remarks that Tamarack is in the Mississippi watershed as well as the Great Lakes. And that's just a comment.
I noticed Darby also asked for a copy of the energy consumption so far. Could you I'm not going to say I'm losing my memory. I'm not that old quite yet, but it does help me when I see requests, and if you send me an email, I can just respond to that email. And if you can't find me on the email address, then I'm sure the organizer of the talk can pass it on, or you can find me on LinkedIn and things like that. There's not many people in the US with my surname, so that's a blessing if you try and find me.
Yeah, we can provide your email to all the participants if you'd like. Rodrigo Carnero says, I'm working in a preferability study for a nickel cobalt laterite project in the Santa Cruz, Philippines. The mining company has received a grant from the USDTA, which indicates that the US government is supporting the development of nickel cobalt project outside of the US territory.
So that's not surprising. The US is kind of moving towards what we might call friend sourcing. So the US actually has an agreement with Indonesia, I believe, as well as working closely with Australia and Canada to secure the supplies of metals that we may not necessarily have in the US. I mean, we should certainly increase, in my 2 cents, we should increase mineral exploration, mining, processing in the US full stop, because there's a lot of potential here. And also, if we do the processing and things like that in the US, we actually retain a lot of value, security of supply, jobs, and so on. But for those metals we may not have in abundance here, then certainly friend sourcing from the Philippines, from Canada, from Australia, from friendly countries that have resources that we could find useful, I think will certainly be an important part of securing domestic or friendly sources of critical and other metals going forward.
Yeah, there's a bunch of other comments here looking for your papers and so forth, and all of these comments and questions will be included in the final documentation of the webinar. Debbie Strusacker has another comment. She says it's worse in Minnesota because these were discretionary leases, not mining claims like here in Nevada, which have a property interest associated with them. So Debbie is very much up on the mining laws and governance. She's our resident expert on that. So if there are no more questions, I think we'll say thank you everybody for showing up, and we really appreciate Simon's presentation, and it was very informative. A lot of people commented that they liked it. So we'll get out information to everybody about how to get copies of that paper and database. And we will have copies of the slides on the website when we put up the YouTube video.